storytelling. And the story starts from the fact that, so we've been here for 3 days, and it seems like, I mean, it's a bit, לא שומעים? It's a bit disturbing that we had essentially one talk about algorithms, or the same algorithm that we've seen over and over again, and every time with just the same algorithm with lots of interesting things to say about it, but the algorithm is the same. It seems like this is a situation which we would like to change, especially since our claim to fame is that you know, there are quantum algorithmic speedups and quantum exponential algorithmic speedups, and we would like to have more algorithms. Now there are a few more algorithms, but in my opinion, this is one of the most important questions, to really come up with much better and new designs of quantum algorithms. And I think this is where mathematicians can get in, and computer scientists. And really, I mean, people have thought about these questions, of course, and these are very difficult questions, but it's sort of clear, right, that we have seen only the tip of the iceberg. So where else can we go? And one sort of hint of where we can go, I think, comes from equivalent models to quantum computation. So I'll say, I don't remember where the slide I had about it is, but let me just say that there is something very special about the quantum model, which does not happen in the classical model. In the classical model, if you remember in my first talk, I showed several models, Turing machine, circuit model, etc. But okay, they're different, but they all more or less look the same. Some local updates, Boolean functions, simple steps, and then things accumulate. Somehow, quantum computation models, there are quite a few equivalent models which look completely different. And each one of these models seem to direct at also a different algorithm. And it looks like it could be very interesting to study these different models and try to come up with algorithms via these different directions. So I'll start my talk with a few slides about this, and then I'll move to a whiteboard talk. So what are the algorithmic challenges? First of all, I don't think we've talked about it almost at all. So the one thing that we should say here is that probably we shouldn't hope for solving NP hard problems, because they're not extremely good reasons for that, but there are good reasons for that. There is the Bernstein-Vazirani result that shows that if we don't understand the inner structure of the function that we'd like to, say, find, so if we don't get access into the inner structure of, say, a given formula, we have no way to find whether it's satisfiable or not, more than quadratically faster using a quantum computer than a classical computer. So there's only quadratic speedup if we don't get into seeing the structure of the problem. Now, so this is called the black box model, but there's so many black boxes around that. Okay, but this, of course, doesn't prove anything, because we do have access to how the formula looks. So there's no proof that BQP does not contain NP, but there's a very, very strong belief. Okay, so if we're not going for NP, at least for now, what are the open problems? So first of all, and this is just sort of telling you a little bit about what problems people looked at. So maybe one of the most, the first problem that caught people's eyes is graph isomorphism. Graph isomorphism, you're given 2 graphs, each of n vertices, and you want to know whether they're isomorphic one to another, whether there's a permutation that takes one to another. And there is Babai's result that gives it a quasi-polynomial time. That's a recent, I don't know, when is it from? 2 years ago, a breakthrough. It was for a long time open, whether that exists. But anyway, is there a quantum polynomial time algorithm for that? And I think Adam mentioned this as this could be cast as a hidden subgroup problem over the symmetric group, but more or less, there's a sequence of papers by Vazirani and Schulman and others that sort of rule out this direction of going through this Fourier sampling, of extending the hidden subgroup problem approach that Adam talked about to the two non-abelian groups, or to the symmetry group. So whether we can solve it or not, we don't know.
What do you mean by quasi-polynomial?
Poly to the log n. So n to the log n. Okay, so here's another problem that's of interest for cryptographers. You're given a lattice over n dimensions, and you want to, you're given another vector, and you want to know if this vector, you want to approximate the distance of this vector from the closest point to the lattice, but the approximation is not exact. The exact solution would be NP hard. The approximation to within a factor of square root of n is the dimension of the lattice. That's a problem that's known to be in NP intersect co-NP. And that's not NP hard. So, or we believe it's not NP hard. So maybe it's a place to start. And people have tried both problems very, very frustratingly and with no success. Okay. But that doesn't mean there's no algorithm. But I'm just saying this is sort of trying to look for problems that are not NP hard, not known to be in P, and that they have some structure, because the algorithms that we have so far, well, everything that we did so far in algorithmically sort of tells us that in order for quantum computation to have an advantage, you need to have some structure. The system needs to see some structure. The quantum computer needs to see some structure, but this structure needs to be such that it cannot be detected classically. Like, for example, the period in Shor's algorithm. Okay, so these problems clearly have very nice structure. We don't know how to access it. Here are a few other problems.
What do you call structure?
So, for example, in Shor's algorithm,
I understand, but here I don't understand.
I don't understand either. I mean, it's sort of, in a very loose sense, for example, this problem is the problem of finding the automorphism group over Sn. This is structure. That's all I mean. Okay, so there are various problems that sit in this set of problems in NP intersect co-NP or close to that. For example, the conjugacy problem for the braid group. I'll talk about the braid group later. But you're given two braids and you want to know if one is a conjugate of the other. There's a cryptographic system based on that. We don't know if there is a quantum algorithm for that. And there's no polynomial time classical algorithm for this problem. And another problem is to detect the unknot. Knots are objects like, not rubber bands, but I don't know, like strings that are closed. There are no floating, dangling edges, okay? And there can be very complicated objects. And we want to know, is a given such a link, is it equivalent, isotopic, to the unknot, meaning just the circle? And that's a problem that's known to be in NP intersect co-NP. In fact, that's recently was found.
Are you saying that all these four structures are related to NP and co-NP?
Am I saying that all these structures are related to the NP intersect co-NP? I'm just saying that these problems all are known to be in NP intersect co-NP, and therefore they seem to be good candidates for quantum algorithms. I didn't get to that. So this is the last problem. Approximate the partition function of the Potts model. I'm not going to define it. Actually, don't know much about it. I mean, I know that that very good approximation, multiplicative approximations, are sharply hard. But okay. So this is a hard problem in certain types of approximations, and I don't know exactly what's known about it.
Just to mention, we don't know the proper isomorphism in co-NP. That's.
Oh, thank you. Yeah.
Thanks, Mickey. I just
that's true. Thank you. Right. Yeah. Please correct me while I'm going, because I'll touch upon many things, and
So these lists are just algorithmic challenges.
Oh, I should repeat what you said for the record, that we don't know that the graph isomorphism is in co-NP, and that's a big open question.
So these are just lists of algorithmic challenges.
Yes. And by the way, it's a very big open question, which seems perhaps accessible to show that it's in quantum NP, the graph isomorphism problem. Okay, so that's just to put things in context. Yes?
Yeah, question about the unknown. So it looks like some kind of continuous object. So how would you encode it in a way so that a Turing machine or
yeah. So how do we encode the unknot, or in general a knot, as an input, because it's a continuous object? I'll talk about this if I get to it towards the end of my talk.
What do you mean about Nash equilibrium? Two-player Nash equilibrium?
Right now, I don't want to mean anything about it. There are problems in Nash equilibrium which are not known to be in P and known to be in a class called PPAD, and it's sort of something where somewhere intermediate complexity. So we are, yeah. Okay, so that's sort of the framework, and one thing the one possible approach towards these questions that perhaps one should keep in mind, because it keeps coming up in various directions, is the inner product. Is the fact that we could possibly, for some of these questions, if we generate certain highly complex quantum states, we could use what we call the inner product estimation, or the Hadamard test, which has come up many, many times here, and also in Sandy's talk, and I think also in Avishay's talk, and I don't know, everywhere. If you have two states that you want to estimate their inner product, you can do that quantumly, easily. And sometimes this is very useful. So I want to just look at this for a moment. And I'm going to talk about black boxes. Sorry, different black boxes, but very simple black boxes. So here's a black box. Boaz, is Boaz here?
Yes.
Okay, so Boaz got a trauma, I guess, and kept saying, for those people who don't like quantum, this and this and this. So if you don't like quantum, which is an empty, you're probably not here, but still, if you don't like quantum, you can forget quantum for a moment.
For those people who have advisors who don't like
yeah. Think of the following classical problem, okay? You're given access to two black boxes. Let's call them pink boxes, so that don't confuse with anything. And these boxes, you're actually given access to a single pink box. And this pink box was drawn from out of two pink boxes, and you don't know which one it was, okay? And the first pink box has some distribution P, and the second pink box, meaning it samples out of n-bit strings, and you can get a sample like that. And then the second one is Q, also a distribution on n-bit strings. And what you have to decide is this. So you have access to both these boxes, and you have to decide. You have access to a box of type P and another box of either type P or type Q. And Q is promised to be either the same as P or of non-intersecting support on the n-bit strings. Okay? And that's all you know about it. Is the problem clear? Okay. How many samples do you need? If all you know about these distributions is this, that either they intersect, either they're the same or zero intersection. So for example, think of P and Q being uniform over half the strings, and either they intersect, either they're the same, or they don't intersect.
But you know the support?
You don't know the support.
Right.
Yeah, so how many samples would you need? If you don't know the support, many. Thank you. That's the right answer. Huh?
Birthday, right?
Yeah, birthday paradox. So you need exponentially many if we're talking about n-bit strings. Okay, quantumly, you need very few. Here's how you do that. So, okay, so suppose you have access now, instead of to these boxes, you have access to two quantum states, which we'll call quantum samples. And these are superpositions over these strings with the right probabilities. And you either have them, so the p's and the q satisfy the same condition. So now you have to decide whether p and q are the same or they have zero intersection in their support. And now what? What can you do? Well, one thing to do is, of course, you can just measure in the computational basis, and then you get a sample from the classical case, and then you go back to the original problem. But that's not what you want to do. What would you want to do? You want to estimate the inner product, because the inner product between the two would be zero if they have zero intersection in their support, and would be 1 if they're the same. Okay? So estimating the inner product here is what you would like to do, and that can be done with very efficiently using the inner product test, the Hadamard test, which you start with, say, p and q entangled with another qubit. So you generate 0 tensor p plus 1 tensor q. In fact, I have to tell you how you generate this state. You don't really know how to generate this state given p and q. What you actually want to generate is 0 tensor p tensor q plus 1 tensor q tensor p. So you're given p and q, and conditioned on the first qubit being 1, you swap them. But it's the same thing. Okay, so you can ignore this if you didn't understand my last line. So you have this state, and we have access to it. So we just apply the Hadamard and measure the first qubit. And if you apply the Hadamard this on the first qubit, this guy goes to this plus this, and this guy goes to this plus this minus this. And now if p equals q, what would happen? The 1 will cancel. This cancels this, and then we have a deterministic 0 on the left side. Whereas if p is orthogonal to q, what would happen? It will just not detect a 0. There's no effect of the 0. If p is orthogonal to q, what will happen is that if we measure the first qubit, it's just uniformly at random, 0 or 1. Okay, and in general, you can easily, that's a very simple exercise, that the probability of 0 of the left qubit, the control qubit, depends on the inner product. So if we're talking about general states, that's the real part of the inner product. Okay, good. So that's due to interference. So we can estimate the inner product efficiently by measuring the left qubit. Okay, so let me just say why inner products or why states are so, if we could generate such complicated states, like the states we talked about before, like given a probability distribution, generate what's called the quantum sample of this probability distribution, meaning just a superposition over the strings with the coefficient being square root of the probability. Okay? Let's call this the quantum sample. So why would that be very helpful? So let's talk about, for example, about lattices. We have this problem with the lattice, and suppose we could generate this superposition. Okay? This is a superposition of all points. This is a high-dimensional lattice, and this is discretized, of course, and each point here is sort of described by many bits of the location, and this is just the amplitudes. Okay? So these are Gaussians around the lattice points. And now, suppose we can generate the superposition, which is sum over all lattice points with Gaussians around each lattice point. Okay? If we could do that, then we could answer the question of whether a vector is far or close to the lattice. Because what we could do is, okay, let me run it again. You see, I have this superposition, and now I can shift it by v. I can shift it by the vector that I want to know whether it's far or close to the lattice. So I shift it, and if v is far from the lattice, then the inner product is close to 0. Whereas if v is close to the lattice, then since everything is periodic, then the inner product is close to 1. Of course, I need to do things so that everything is finite, but okay. So Okay, so if you can generate such a superposition, you solve the shortest vector in a lattice problem by estimating the inner product between these two states. Okay, but this seems like an easy thing to generate, no? Yes.
It takes exponential time.
Well, I don't know that it takes exponential time, but I just want you to notice that that you can.
Sample, I mean, classically, if you could erase bits, you could just sample randomly.
Exactly. So classically, the probability distribution that underlies this, meaning after I measured this, that probability distribution is easy to generate. Sample a point from the lattice and then walk by a Gaussian weight. Okay? So that's easy. But the problem is that in quantum we have this חוץ סביבה. How do you say that? Environmental issue that we cannot get rid of garbage. It's very hard to get rid of garbage, like in Israel. And so the problem is that we can generate a superposition over all points in the lattice. All points in the lattice, and the shift of the L plus the shift, but we can't get rid of this L. Okay? And likewise for graph isomorphism, we can generate all permutations in Sn tensor the permuted graph. And if we could get rid of this permuted graph, then for two isomorphic graphs, these two states will be the same. But since we have this sigma here written down, we cannot do that. So we don't know how to erase, we don't know how to generate these states. Okay, so this is, yeah.
We don't know, is it negative or positive state?
You tell me.
That just means that you
Let me.
know, or there is some theory which tells you impossibility.
No, so let me repeat the question. Is there a theorem that tells me anything about the impossibility of this?
In general, not for particular problem, but wide class of problem.
Yeah.
Prove impossibility.
Well, okay, is there sort of a general thing about a wide class of problems that we could say this is unlikely? I have a paper with Amnon, an old paper, that says that if we could do that sort of quantum sample from any probability distribution that we could efficiently classical sample from, we could solve statistical zero knowledge. That's a class. But we don't know that we cannot solve statistical zero knowledge. But it's I don't know. You take it as you wish, if it's likely or not. Okay, so.
Is there like a general kind of trade-off in the sense that if you need to erase k bits, you can do it with an overhead of 2 to the k time?
Just repeat.
If you need to erase k bits, you can do it with 2 to the k time. Well, this is sort of a one-way function, right? If you could compute the inverse function, you could erase sigma. But so yes, I mean, if you have.
But then you could do graph isomorphism.
Yes, but then you could do graph isomorphism. Okay, so. Yeah.
Is there an oracle separation between SDK and BQP?
This is where I move to the board. That if that guy behind. אמנון, אתה יכול להגיד לו? Sorry, can you continue the question? What was the question?
I was just wondering if there's an oracle separation between SDK and BQP.
Well, there is Scott Aronson. Is there an oracle separation between SDK and BQP? And there is again an oracle. Yeah, there is something by Scott Aronson that says that. Yes. For the collision problem. That's a very important. Thank you. Okay. Yeah. Good. Okay, so let's see a few. So I want to tell you a little bit about a few models of quantum computation, which which could hint towards addressing these questions or towards some advance. Okay, so really the title of my talk was that there are several models of quantum computation that are equivalent. So somehow I missed the slide. I don't know where it left, where it went. But these 5 models were, one was a Riemannian geometry one. And I'm not going to go I'm not going to go into this. I don't have time. And I don't have the knowledge also. But this is a very nice sort of translation that Michael Nielsen did and other friends joined of looking at, of defining a metric, Finsler metric, on the unitary group such that it sort of favors 2 qubit gates. And then the geodesies on this manifold are exactly, it can be shown that with a science paper, that these are the minimal length, the number of gates that are needed to express the unitary are exactly the length of this geodesic. Okay, and this is interesting. Possibly, I don't know. People in the it from qubit crowd doing quantum gravity got.
If you consider Riemannian metric, of course it doesn't give you what you want, but could you then effectively estimate geodesics? It's much simpler object, Riemannian metric than Finsler.
I don't know. Let me just repeat the question. It's an open question. If you consider Riemannian metric instead of this metric, can you actually estimate the length of the geodesic? I don't know.
Invariant, right? Invariant Riemannian metric.
Yeah. So invariant Riemannian metric. I don't know. So this goal, by the way, of this talk is really to put the open questions clearly on the board or wherever. Okay. So that's one thing. There's another one that's called measurement-based quantum computation. By the way, I put links to relevant 2 or 3 papers for each one in the abstract, so you can look at that. All the names, the relevant names, etc. are there. Measurement-based quantum computation is a very interesting model of computation, which is sort of more similar to the model to the circuit model. Except that all computations are done by measurements. You just prepare a highly entangled state on a grid. Actually, it's not so highly entangled. It's easy to prepare. You just prepare states of the form plus, tensor, plus, tensor, plus, tensor, plus, and then you apply some simple gates, controlled I, locally, depth 1. You have an entangled state, and then all you need to do is you need to measure qubits one by one at a time. And the only thing that happens here is that you measure a qubit, and then from the result of the measurement, you sort of learn what's the measurement basis that you need to use in the next step. And that turns out to be universal for quantum computation, and it's used in many new results, but I won't go into that. Okay, now there are 3 other models that I wanted to mention. One is adiabatic computation. This is tightly related, I'll explain what that is. This is tightly related to a model of quantum walks. Both are universal. And then the Jones polynomial. That has to do with knots. Okay, so let me spend a few minutes on each one of them. Okay, so adiabatic computation. Adiabatic computation is a model that sounds very different from circuit model, and it sort of is highly motivated by this attempt to generate quantum states, complicated quantum states, because it talks about ground states of Hamiltonians and their spectral gaps. So where does it come from? It comes from the Adiabatic Theorem, which is a famous theorem in physics. Yossi is an expert on that and can explain everybody who wants the details of this. Adiabatic computation, Adiabatic Theorem says this. It says that if you start from a Hamiltonian H0. And you modify it very, very slowly. Actually, let's make it not a direct path, a straight path, but a path to H final. And you may, or to H, let's call it H0 and H final. And you make sure that all these Hamiltonians have a unique ground state. For now, let's just make sure A. And you make this modification very, very slowly, starting from the ground state of H0, ground state of 0. The Adiabatic theorem says that in the limit of t goes to infinity, when you apply the Schrödinger equation with these h's, you get to this final Hamiltonian, GST, GS of final. Okay? And how would we use that in order to actually perform a computation? Well, Farhi et al. In the early 2000s suggested to use this in as follows. Well, let's encode a problem in this final Hamiltonian. What would the problem be? For example, let's take 3 sat. And let's make the ground state of the final Hamiltonian be the solution for 3 sat. We saw how to do this, right? We saw how to do this in Sandy's talk yesterday. So this final Hamiltonian could be a diagonal Hamiltonian, and the diagonal terms would just be the number of clauses that are violated for a particular assignment. And the ground state here is what we're looking for, right? This is the satisfying assignment. So
ground state is not necessarily one-dimensional.
That's true. That's true. But in fact, in complexity, you can assume that you can show that it's the same, almost the same hardness. So then one idea would be to start from a Hamiltonian H0, which is a sum over minus over all tensor identity on the rest, over all I. And this Hamiltonian gives energy penalty, with the same language that Sandy said, gives energy penalty to the state being minus for each qubit. So actually, its ground state is just plus. Okay? So at every qubit, the ground state is plus. So basically, the ground state of this guy is just a superposition over all I. I goes from 0 to 2 to the n minus 1, where this is a binary representation of I. Yeah? So this is normalized, of course. Okay, so this is the ground state here, and this is easy to generate, of course. So we can start here. We can adiabatically move to this ground state, and voila, we have an NP algorithm. So what's the problem?
T could be large.
T, by the Adiabatic theorem, needs to be extremely large, and if we want to make it into a computational model, we need to somehow put bounds on T. So what would T be, so that instead of needing to go for infinite amount of time, what we need is just to go for finite amount of time, T. So by massaging a little bit the Adiabatic theorem and looking into it, one can get convinced that, that if the spectral gap of all the Hamiltonians along the way is at least, spectral gap being the distance between the lowest energy and the second lowest energy. So if that spectral gap is, does not close, if it's at least inverse polynomial, then we're fine. So the time needs to be something like 1 over gamma squared. Now this 1 is not a 1, it depends on the derivative here, etc. But if everything is nice, that's what happens. Okay, so T is polynomial if the spectral gap along the way is large enough. Yes? We are applying a time-dependent Hamiltonian. I'm sorry?
This series in the expanded mixing, for example, but this is just like a random walk from H0 graph to an H0 graph.
Is it like a random walk from H0 to HF? Is that what you're asking?
Mixing to HF, like he said, T will be infinity to mixing to HF. That's the idea.
I'm not saying, I didn't say mixing. I was just saying that if you start from this ground state, the system, the quantum system, tracks slowly the instantaneous ground state of each Hamiltonian, and therefore it reaches the ground state of the final Hamiltonian. And that is true if t goes to infinity, but it's also true approximately if t is larger than 1 over gamma squared.
So suppose you know that for H final, the gap is large.
It is
Could you
It is large. Here it's large, it's 1.
No, it's 0. Suppose you know the same.
Both of them.
For example, for final. Do you know that there is
No.
buff?
No. So the question is, suppose I know that the gap here and the gap here are large. Do I know that there is a path that doesn't close the gap? I actually modified your question a little bit. If I just take a converse combination between H0 and H1, that definitely does not determine, I mean, you can have situations where the gap closes to exponentially small, whereas you can have situations where this doesn't close. Whether there exists a path which doesn't close the gap, I don't know. I know. That's why I'm asking it. David said that it's a kind of a mathematical problem. I don't know. It might not be very difficult, but I don't know. I don't know about the connectivity of
If you don't put a condition on the length, then most probably it's easy.
well, if you don't put a condition on the length of the path, it's probably an easy problem. I don't know how the space of how this space of Hamiltonian is connected.
I think that this should be known.
Okay, this should be known. Great.
But Dorit, we could
yeah.
say that we don't hope for finding one efficiently, except that's a very unlikely event, right? That would imply that BQP contains.
Yeah, we
NPs.
don't
Yeah.
we don't know that. What Or said is that we cannot hope to find a path like that efficiently, because that would prove that NP is in BQP. In fact, if the existence of this path would prove that it is in BQP slash poly, so maybe we shouldn't hope for that either. But okay, so I'm just throwing some questions here. I don't want to dwell into that. Okay, last questions about this. Yes.
Just want to clarify what is the timing? Does it mean
What is the time? So here, here there is a parameterization S that goes from 0 to 1, and H of t is, so if H of t is this guy, then the Hamiltonian that if I define H of S to be 1 minus S times H of 0 plus S times H of 1, then I actually implement this evolution, but with H of t being H of S being H of t divided by the time. Okay? So, but this is technical. Okay. So, good. So this is Adiabatic computation. This seems like, okay, so this closes. This, we know, at least in several studied examples, for NP-hard problems, this closes. So that doesn't work. So does Adiabatic computation lead us anywhere? We don't know.
This proves that if the spread gap in the local one has some gap, then you get passed to the end state. Is it the theorem?
Oh, this is Yossi, it's Kato, right? What's the Adiabatic? Oh, the analysis with respect to the 1 over gamma squared. I don't know exactly who did it first.
At least I know Beth-Ruskay and Zeiler, I think.
Okay, Beth-Ruskay and Zeiler. Okay, so. Okay. So just to say why this model is actually universal for quantum computation. It looks like a very different model. Why is it universal? We would like to have this final state be the final state of a quantum circuit. If we could do that, then that's great. I would generate adiabatically the final state of the circuit and measure it and get the result. That's not how it works, because to find a Hamiltonian whose ground state is the final state of a circuit, how do I write down such a Hamiltonian? So which Hamiltonian should I use? By now, you should be able to answer. Which Hamiltonian should I use? I'll give you a hint. Sandy's talk. So the final Hamiltonian could be the Hamiltonian that is used for the circuit to Hamiltonian construction. Going from the circuit to the Hamiltonian, you can have a Hamiltonian, a local Hamiltonian, whose ground state is the history state of the computation, whose unique ground state is the history state of the computation. And meaning the superposition over gamma t, tensor t, for all the time from 0 to t, normalized. So if you can adiabatically move from some easy to generate state, product state, to that state, then we're done. So all that we need to do is to show that the spectral gap between this or something similar to that, whatever. So what we actually need to do is we need to start with H0 being a Hamiltonian whose ground state is gamma 0 tensor 0, where gamma 0 is just a tensor product. So that would be a state which is easy to nail down by local constraints, because it's tensor product. You just penalize x not being the right thing. And all you have to show is that the convex combination between this Hamiltonian that projects on everything orthogonal to this, not projects, but penalizes everything orthogonal to this, and this Hamiltonian that has this as its ground state, that the spectral gap is nice. And this is not very difficult to show using a Gershgoner disk theorem and some combinatorics. It's not easy to. It's not difficult to show that the spectral gap behaves nicely. It starts from the fact that the spectral gap of this Hamiltonian, like Sandy said in her talk, is so this Hamiltonian, when looking at it in the basis of these gamma t's, if you remember Sandy's talk, it looks like 2 minus 1 minus 1, 2, etc. Or sorry, 1 here and a half. And we know how to analyze the spectral gap of this guy. This is inverse polynomial. So this is good. And the convex combination of this and this simple Hamiltonian also can be shown. So adiabatic computation is universal. So far, there was no algorithm that came out of the adiabatic computational model, even though it seems like it's close to Markov chains. It calls for ideas coming from that direction. We don't know. One place where we do know is a model very close to adiabatic computation, and that's the model of quantum walks. Quantum walks is instead of, yeah?
Was this the way, the proof that you just explained, was that the way it was first proven? That adiabatic and circuit model like quantum?
Yes.
Okay.
This is in our paper.
I didn't know.
Yeah, sorry.
So
Matthias asked, is this the way it was first proven? And yes, this is the way it was first proven. This is this convex combination between the first Hamiltonian and the last Hamiltonian is showing that. Yeah. Okay. A very similar or related model, which may be easier to work with, is the quantum walks model. What's the quantum walks model? You have a single Hamiltonian coming from a graph. So you have some graph. And your Hamiltonian is the adjacency matrix of this graph.
The graph is just simple graph, right?
The graph is the graph. And, you have the adjacency matrix of this graph, and the nodes of this graph are n-bit strings. And what you apply is e to the I h t. And that's the quantum walk model. Okay? And that is shown by Charles to be universal. Also, with the proof of this is much more difficult than this thing. But in this model, we...
I don't understand this state. Universal means what is the statement? You produce this one parametric subgroup from graph. Now, what are you asking?
What I'm asking is whether, for any quantum circuit, it is possible to design a simple to implement Hamiltonian, meaning a Hamiltonian such that if you're given two nodes like that, you know what is its value, such that if you run this, if you evolve this by Schrodinger's equation and you measure at the end, you can get the result of the computation. I'm sorry?
For what initial data?
For whatever initial data. I mean, so this is a technical question. You can hide the input into H if you want. Or you can initiate the state to be your input.
So, for example, there is a mapping between a circuit and a graph.
There's a map between a circuit and a graph. Yes. Yes. Right. And the way it works is by basically taking gates and replacing them by gadgets of graphs with scattering into these gadgets gives you various nice coefficients that sort of mimic the unitary evolution. Forget what I said, but okay, so it's a nice proof. But what I wanted to say is that in this model is we do have an exponential speedup. And this is very different than what we know. Wow, what are we doing in time? Okay, so I'll just say it in one. Huh?
At least we understand.
Okay, so yeah, but we have a tour to a UNESCO site. Okay, we'll take until 1 and stop. Okay, so just to mention, there is a beautiful algorithm that gives an exponential speedup in the black box model, meaning it is provably exponentially faster in the black box model, in the same sense that Avishai was talking about, where what you're given is access to something like this binary. So the graph that we're talking about here is now a binary tree glued to another binary tree, like that. And the gluing is by some random permutation. And you can walk on this graph by an access to an oracle, meaning if you know the name of this node, you ask the oracle, who are my neighbors, and it gives it to you, and then you can walk. And your goal is, given the name of this node, to find the name of this node. And this is an exponentially sized graph, but it's highly symmetric. This is n, or 2n, but of course the number of nodes is exponential because it's a binary tree. Randomly performing a random walk here would just get caught in all the middle here and will get lost. Quantumly, you just scatter all the way through, just in any direction, and you get from here to here in polynomial time. It's a beautiful algorithm. I recommend reading it. Okay, but this is an exponential speedup using the quantum walk, and it's a different thing. It's not Shor's algorithm. I want to say 2 minutes. This is Childs, Spielman, Doherty helped me out. Cleve. Cleve is there. Farhi Gutman. Right? I think I covered all of them. Okay. And again, this is maybe it's linked or maybe it will be linked to in this set of papers. I want to spend 3 minutes on another beautiful model which is equivalent to the quantum model. Again, seemingly completely different, and that's the Jones polynomial. What's the Jones polynomial? Let me breathe just for a second by erasing the board. Actually, okay, so what's the Jones polynomial? The Jones polynomial is a knot invariant. I spoke already about knots. These are these strings tied without dangling edges. It's just links. And somebody asked how I can actually present them. So I can just project them in 2D. And here is a way to I don't know, I'm just inventing something. Okay, so here is a link. And that's the 2D diagram of this link. Is this link the unknot, by the way? Yes. It is. Okay, so I want to somehow understand this, these knots, such knots. And one ingenious way that Jones came up with is to assign, I mean, this was a method that existed much before, but Jones assigned certain polynomials to such knots, such that isotopic knots are given the same polynomial. It's actually a Laurent polynomial. Okay, so that's denoted V of t.
Before that, you can just see that you can make this discrete, but you can just look at the intersection point.
Yeah, I meant to say that, I forgot. Yeah, so this is the 2D diagram here, of course, can be given as input because it's discrete, because we don't care about the isotopies here, we only care about the intersection points. Thank you. Okay, so the theorem that I want to tell you about actually comes from another model, which is less accessible to me, at least, the topological quantum field theory model, which is also equivalent to quantum computation. And this is essentially a translation of that into combinatorics. And so the theorem says that the following problem is BQP complete. You're given a knot with n crossings, and you want to compute the Jones polynomial of this knot at the some kth root of unity for k some integer. I'm sorry?
T equals.
Yeah, t equals this. For specific case, it's easy, but for most case, this is sharply hard. What you want to do is to compute the approximation of that additive approximation. And I'm not going to tell you what the additive approximation, what the approximation factor is. Approximation window. What's the idea? Why is this BQP complete? What's the relation between this and quantum computation? Well, it turns out that you can, the whole idea is that this beautiful picture can be assigned the structure of an algebra. And this algebra is called the Temperley-Lieb algebra. What's the algebra? This is made of, so actually, let's look at this as what's called a closure of a braid. Here's a braid. Something like that with 3 strands. You can have n strands and with crossings. And again, things are isotopic except for, so everything that you can move without changing the pegs here is the same braid. And there are relations called the Artin braid group relations between these generators. The generators are these crossings. And this would be a link. If I close this, this is the Plot closure. You can also close it differently as a trace closure. And okay, and then how do you assign Temperley-Lieb? How do you assign to this an algebraic structure? Well, you can represent this braid group in the following algebra generated by these pictures. Okay, so pictures like that. This is, if this happens in the ith strand, I'll call it EI. Why is it a group, or why is it an algebra? Of course, the braid group is a group because you can just stack things on top of each other. And this is also something that you can stack on top of each other, except you might encounter a loop. Okay, so when you stack this on top of each other, EI squared, you get a loop. So the Temperley-Lieb algebra is accompanied with a variable, a parameter, called d, which is the loop value. And then when you encounter a loop, you erase it, and you gain a factor of d. So this is equal to d EI. Okay? And with this structure of an algebra, if you have a representation for the Temperley-Lieb algebra, which is, if it is a representation of this, then since this can be embedded can be represented in the Temperley-Lieb algebra, which in a way which I'll show you in a moment, that would give a representation for these links. What does it mean? How can I represent this here? Well, every such crossing I can write as A identity plus A this thing, plus A to the minus 1 this thing. Okay, and then the other crossing I'll write in the opposite. This is a to the minus 1, I plus a this. And a is related to d in some way. I don't have time to write it. Okay? Let me write it. Okay? So this is a Temple-Lieb algebra. We have the relations. The relations are the relations between the generators are the natural relations that we would have. And this is the braid group, and it can be represented in the Temple-Lieb algebra. And if you have a representation of this, which is a representation into matrices, then it induces a representation on these guys. Okay, what's the? I'll end in saying how is this giving me an algorithm? The Jones polynomial can be represented as some kind of taking this link and opening it up with these rules. Whenever you open each crossing up with these rules, you get, after you've opened all crossings, you get a bunch of loops. Each loop gets the value d. And however, you have many ways, you have 2 different ways to open each crossing. So you have exponentially many states that you get, exponentially many pictures. And you have to sum them up. That's the Jones polynomial. And it turns out, and that's the key point that I wanted to say, this is why I'm trying to make to this point. The key point is that somehow, by finding a representation, this is called the Temple-Lieb algebra path model representation found by Jones. By finding a representation here, you manage to, that you can implement by a unitary circuit, you manage to somehow save this exponential sum because of changing the order of summation. So what happens here is that you sum over the exponentially many possible ways to open things. Instead of that, you have a representation for each one of the operators here, each one of the generators here, and you can just multiply them. They're just polynomially, there are n of them or m of them, poly n of them. And once you multiply them, it turns out that the trace of this guy will be equal to the Jones polynomial at that point. So this is a bit too much to digest, but I just wanted to give you a hint of what goes in there. And I personally think that this structure of looking at representations of algebras that sort of extend combinatorial structures that are of interest to us should be possible to do in other contexts. So I think we're ready for the UNESCO site. Maybe.
Can I ask a simple question?
Yeah, maybe 2 questions. But okay.
Where is qubit or operator? Where is qubit or information unit in this Temple-Lieb algebra?
Where is what?
Like where is qubit or where is quantum?
Where is the quantum?
Yeah.
Good question. It didn't enter. I mean, what entered here was that there was a unitary representation of this Temple-Lieb algebra. And the point is that this representation of the Temple-Lieb algebra was on objects called path. I really didn't have time to talk about it. It's called the path model. And this path are path on lines. And these paths can be translated into bit strings. Okay?
So something you missed is the...
Yes.
Okay, I have a question. You see, there is a kind of wait-and-see way to compute Jones polynomials in terms of a infinite-dimensional Feynman integral.
Infinite-dimensional?
A Feynman integral, kind of infinite-dimensional integral. Now, there's a lot of, in physics, people approximate many questions, these computations, by finite dimension. Did you try to look whether this kind of computation of Jones polynomials through integration gives some new way to deal with it?
No. No, I don't know. I don't know that it was tried. I don't know.
Okay. Okay, so let's thank Dorit.
No, we should all pick up, whoever goes to the tour should pick up a sandwich.